All right, so this final video today gives us a nice example of how to actually use this complicated looking formula that we just derived. So the point of this formula is that it allows us to look at the initial state of our system and figure out, after this perturbation described by h prime of t acts, what would the final state look like? What would the state look like at time t? And so our application is going to be back with the original motivating example that I talked about. Let's say we have a hydrogen atom, and so maybe at time 0 we have some electron in the ground state, and so we have this state psi100. But now all of a sudden comes along some electromagnetic wave, and so our h prime of t is going to be some extra term in the electron's Hamiltonian that takes into account the interaction with that electron, between that electron and the electromagnetic field. And so what we want is, let's say we want to find the probability that if we measure our electron at some later time t, we want to find the probability that that will have made a transition to some other excited state. So probability of making transition to, say, psi n l m. Okay. And so let's just do a slightly more general problem here. So we will say that in our setup here, suppose that we just have one of those c's not 0 initially. So in this case, what we have is c a equals 1, where in our example, a is the 100 state. And we have c for b not equal to a, so for all the other states, that would be equal to 0. And now what I want to know is, after time t, what is the probability that we're going to be in some other state b? So probability of finding state b at time t. And so that's just going to be the coefficient cb of t squared. And so here's where we can use our result for cb of t. Okay. And now it simplifies a little bit because we've assumed that cb of 0 is 0. We're talking about a state which is not our original state. And so then we can basically ignore that first term. And so our probability is then just going to be the square of this second term here. So what we find is that PB of t would be equal to CB of t squared. And then this is approximately, because we're just going to keep the expression at first order in perturbation theory, approximately equal to 1 over h bar squared times, and now this entire expression simplifies because there's only one value of n for which Cn of 0 is not 0. Okay, so that's only the value n equals a. It's the ground state in our hydrogen example. And so this sum right here, it only has one term in it. And so, whoa. So then what we have is an integral from 0 to t of dt1. And then I'm going to make the expression look a little bit simpler by introducing introducing a new notation. So omega BA, so that's just going to be the energy difference, EB minus EA divided by H bar. So that's going to be a frequency. And then we have that multiplied by the matrix element H prime BA, and that's it. And so actually to understand this transition probability, we only have to compute one matrix element, and that's the matrix element. So this guy right here is the matrix element between H prime of T, between our states psi B that we're interested in as a possible final state, and our initial state psi A. Okay, and so that's the full expression for the probability. In our hydrogen example, that would be something like NLM times whatever our perturbation is times the ground state. So we would have to compute that one matrix element. That would probably involve doing some integrals. Then we evaluate that frequency, which is just the difference in energies between our two states, between the initial state and the possible final state. Then we actually do this integral here, square it, and divide by h bar squared, and that gives us the probability that we're going to find our state to have made a transition to some other state B. Okay. And so that's a very practical formula, and we'll do some examples in the homework for how to use that. And now the total probability, sometimes we want to know, like, what is the total probability that we'll have made a transition to some other state? So this is the final thing. The total probability of making a transition of course is then just the sum over all the possible final states. So P total, just the sum of all the states B not equal to A of CB of T squared. Okay, and so in that case, to figure out that, you would need to look at all the non-vanishing matrix elements between your original state and then some final state, calculate the probabilities, and add them up.